So now we have something that's being dropped, a ball that's being dropped, and a light shining down on it as it's being dropped. And we want to know how fast is its shadow moving along the ground at 1 second later. This is actually kind of a hard problem to think about at times, because you're not used to setting up a problem like this yet. So let's look at how you would set one up. Well, we have the ball up here at time 0, and it's dropping straight down. 1 second later, it's in the line of sight of this light, and the shadow here is going inwards as the ball is dropping. So if we call this distance up here s, how far the ball is dropped, and we started at the same level as the pole over here. This distance here would actually be 50 minus s. It's not going to create a shadow if it's above anyways. So let's see here. If we call this whole distance x, then this distance is actually x minus 20 for us, for our problem. We see that here these two angles are 90 degrees, and this angle is shared between them. So we have a similar triangle set up by angle-angle similarity from geometry. So what we're going to do is we're going to set up proportions real quick. We're going to say that this 50 is to 50 minus s is proportional as the distance. Let's see, that was big triangle to small triangle, so we're going to go big triangle again is x. The small triangle we said was x minus 20. If we cross multiply this out, 50 times x minus 20 is 50x minus 1000 equals x times 50 is 50x minus sx. So if we solve for, let's solve for s. Now the 50s will cross out when we subtract it. If we divide by negative, well, let's solve for x, since I think that's what we're trying to find, how fast the shadow is moving. Shadow's on the x anyways, so let's solve for x. We'll divide by negative s, so x is 1000 over s. So how fast is it changing? We're going to do ex dt is 1000, well, this is really 1000 times s to the negative 1. So our derivative would be negative 1000 over s squared, or s to the negative 2, times the derivative of s with respect to t. And since we're assuming that the distance for s is 16t squared, we want t to be at 1 second. We're going to be able to say that s, therefore, is at 16. 1 squared times 16 is 16. So we can plug in that. And also, if we did a derivative with respect to time of this function, ds dt would be 32t dt dt, but dt dt is 1, so if we know t is 1, we're going to get our ds dt value is 32, and we can plug that in. So we're going to plug all that in to figure out how fast is the velocity of the shadow moving, or how fast is the shadow moving, I should say. So negative 1000 s squared is 16 squared times 32. So if you pull out a calculator, you should get that it's moving negative 125 feet per second. Now that's the end of the problem.